I will chart that represents the step-by-step operation of our closed-loop digital control system using Labview and the Qube Servo. This flowchart illustrates how the system takes a user input, compare it with real-time feedback from the motor, and adjust the motor's position to achieve the desired output. The process begins with the start block. This is where the system is turned on and the Labview is launched. The system gets ready to begin communication with the hardware and waits for the user to enter a desired angle input. Next, the system initializes the hardware in the loop or HIL communication. This step is essential for establishing a real-time link between the Labview software and the NMK31203 hardware. With this connection, Labview can read sensor data from the encoder and send motor control signals to the Qube Servo. Once communication is established, the system starts reading encoder counts from the Qube Servo. These counts represent the current position of the rotating inertia disk. The encoder measures how much the disk has rotated and sends the information back to the system in the digital count values. Because the encoders give the position in counts, we need to convert these values into radian. A standard angular measurement, this is done using a feed skein, typically multiplying the count by 0.00307. This gives us the actual angle of the initial disk in radians, which will be used in the control calculation. Meanwhile, the user provides an input through the Labview front panel. This input is the desired angle of rotation, usually entered in degrees. For example, if the user wants the disk to rotate to 90 degrees, that becomes a reference input for the system. To ensure both the input and the feedback are in the same unit, the input angle in degrees is converted to radians. Now that both the input and feedback are in radian, the system will compute the error, that is the difference between the desired angle and the actual angle. These error values tell the system how far off the current disk position is from the target. A larger error means a greater distance to cover, while a small error means the disk is close to the desired position. Using this error, the Qube servo motor automatically rotates the initial disk toward the desired angle. The motor adjusts its position gradually based on the feedback it receives. As the disk rotates, the encoder constantly updates the current position. This adjustment continues in real time until the disk reaches the target angle and the error approaches zero. Throughout the process, the system displays the output signals on the Labview front panel. There are three main outputs: the motor voltage, which shows how much electrical signal is being sent to the motor based on the error; the actual disk position as measured by the encoder and converted to radians or degrees; the step signal, which is the input set by the user. These three outputs are shown on graph in real time, allowing users to monitor system performance and stability.
Hello, I'm going to explain how we control the Qube servo motor based on this block diagram. First, we start with HIL initialize. This block starts the communication between Labview and the MyRio hardware. It prepares the system to begin reading and writing data to the motor. Next, we have the CLHIL read block. This reads the current position of the motor using an encoder. The value we get here is in encoder counts, not yet in physical units like degrees or radians. Then, we move to convert to radians. Since encoder counts are not very intuitive, we use a gain block to convert those counts into radians, which are more useful for angle measurements. After that, we have the user input. This is where the user enters a desired angle in degrees, but since the system works in radians, we convert the input angle to radians using another gain block, which is labeled as gain 2. Now, comes a very important part, which is summation gain. This block compares the desired angle from the user with the actual angle from the encoder. The difference between them is the error signal, how far off the motor is from the target. Based on this error, the motor voltage control block generates a suitable voltage signal. This voltage tells the motor how much and in which direction to move, so it can reach the target position. Then, we have CL-HIL right. This block sends the voltage signal to the motor via the MyRio, making the motor move accordingly. At the same time, we have the position display. This shows the input angle and the current motor position on a graph, so we can monitor how accurately the motor is following the user's command. Lastly, we have the stop button. When the user presses it, the system stops running and the simulation ends safely.
Now, let's move on to the pros and cons of our control system design based on the Labview block diagram. This evaluation helps us understand both the strengths and the limitation of our approach. First, simple and easy to follow design structure. The block diagram we implemented is straightforward. It includes clear steps like reading the encoder, converting units, calculating the error, and writing output to the motor. This simplicity makes it easier to troubleshoot or explain later. Second, fast signal processing through HIL integration. By using HIL functions like HIL read and HIL write, we get minimal delay between data input and output. This ensures the control system is responsive and fast enough for real-time operation. Third, we have easy conversion from encoder counts to radians for unit consistency. We use gain blocks to convert encoded tick values into radians and also to convert user input from degrees to radians. This ensures both values are in the same unit, making calculations and control more accurate. Next, we proceed to the cons of the system. First, we have no PID control use. This may lead to overshoot or slow response. Our design currently uses simple proportional control. Without a PID controller, we can't fine-tune the system behavior. This might cause the motor to overshoot the target or take longer to settle at the desired angle. Second, we have no noise filtering. Encoder signal may be unstable. We haven't included any filtering blocks in the diagram. If the encoder gives noisy or fluctuating signals, the system could behave erratically or keep adjusting unnecessarily. Third, we have fixed gain tuning, which is not adaptive to different conditions. Our gain values are hard-coded. If the motor load changes or we use a different motor, we need to manually retune the gains. The system doesn't automatically adapt to those changes.
Although well using a simple proportional controller, there are several important improvements that can be made to increase its accuracy, stability, and overall user experience. These enhancements will not only improve performance but also make the system more robust and user-friendly for both technical and non-technical users. Implement ID controller. Use only a proportional controller, which adjusts the motor based on the difference between the desired angle and the actual angle. While this works for basic control, it may not always bring the disc exactly to the desired position and can sometimes cause overshooting or slow settling. To improve this, we suggest implementing a PID controller, which stands for proportional, integral, and derivative. The proportional part reacts to the current error. The integral part accounts for past error, helping the system eliminate steady state errors, while the derivative part predicts future errors and helps smooth out the movement, reducing overshoot. By combining all three components, the PID controller provides a more accurate, faster, and stable response. This will help the Qube servo disc reach the exact angle more precisely and respond better to changes in input. Second, add signal filtering. The encoder provides real-time feedback on the disc positions, but sometimes the signal can be noisy due to electrical interference or vibration. This can confuse the controller and make the system behave less smoothly. A low-pass filter can be added in the software to smooth out the encoder signal. This filter allows slow, meaningful changes in position to pass through while ignoring fast, unwanted noise. As a result, the system will be able to respond more accurately and consistently to actual movements. Third, auto-calibration feature. Currently, the system assumes the disc is in a known starting position when powered on, but this isn't always reliable. If the disc is accidentally moved or starts from the wrong angle, it may affect the accuracy of the system. An auto-calibration feature would solve this problem by automatically aligning the disc to a fixed reference point during startup. This can be done by rotating the disc to a mechanical stop or using a known encoder reading. With this feature, the system would always start in the correct position, improving reliability and reducing the chance of error. Fourth, improve user interface. The current user interface requires the user to manually input the target angle each time, which can be slow and inconvenient. To improve usability, we propose adding preset buttons like 0 degree, 45 degree, 90 degree, or a slider that allows the user to quickly select the desired angle. This will make the system easier to operate, especially for demonstrations or repeated testing. It also makes the system more accessible to beginners or non-engineering users. These improvements will make the system smarter, more reliable, and easier to use. They represent logical next steps for anyone looking to expand this project into a more advanced and user-friendly solution. Developed and tested closed-loop system to control the Qube servo motor. The system performed with reliable accuracy and stability. With further enhancements, it has the potential to become more adaptive and user-friendly.